Welcome to this video lesson, which is the first part of a two-part series on two-dimensional lines. The main concept that you have to know for this video is vector operations. Let's start off this series on lines with an example. Here we have a coordinate system labeled east and north. The north is going to be our y and east is going to be our x. We're going to have a boat which starts at position A, which is 150 kilometers east and 800 kilometers north, and it's going to go towards direction R, point R, and R can have any position. We can give this a velocity v, which is 40 kilometers per hour in the east direction and 10 kilometers in the south direction. Note that velocity is the rate of change of displacement. So in this case, it's displacement over time, and that can be rearranged for the displacement to be velocity multiplied by the change in time. And that means the displacement from A to R will be velocity times delta t. We can break this down into the x and y component. In the x direction, the displacement is equal to the final position in the x minus the initial position in the x direction. We know that the displacement in the x direction is going to be the velocity in that direction multiplied by delta t, and we're going to put that into the equation. We're going to add xa, or initial position, to both sides, and we're going to get x in the final x position is equal to the initial x position multiplied the velocity in the x direction times delta t. We can do the exact same operations in the y direction, and we will get the final position is equal to the initial position plus the velocity in that direction multiplied by the change in time. And connecting these two, or putting them together, we will get what's called a parametric equation of a line which is connected by points A and R. We can also write this in terms of vectors, so we can have a position vector A originating from the origin and terminating at point A, and we can have position vector R which originates at the origin and terminates at point R. Now position vector R is going to equal to position vector A plus vector AR, which is also equal to the velocity multiplied by the change in time. Note that change in time is also represented by other variables in whenever we're writing lines, so it could be t, lambda, u, mu, or many other symbols. We'll use symbol t, so position vector r is equal to position vector a plus t multiplied by the velocity vector, and this is called the vector equation of a line. Note that position vector r, to find it, we will take the x and y coordinate of point R and subtract them by the x and y coordinate of the origin, which is 0, 0. So in this case, we will get x, y, and that will equal to position vector A, which is going to be x naught, y naught, that's the original points, plus t multiplied by the velocity vector, and our velocity vector is going to have an x component and it's going to have a y component. And this is another form of writing the vector equation for a line connected between 2 points. For our example above, if we had point A at 150 and 800 kilometers and velocity was 40 kilometers in the east, 40 kilometers per hour per east and 10 kilometers per hour in the south direction, and the change in time was 2 hours, then the x coordinate of our value is going to equal to the initial x position plus the velocity in the x direction times delta t. The initial position in x is 150, velocity is 40, and the time is 2, so that's going to equal to 230 when we add them all together. We can do the exact same operations for the y direction, so the initial position here 800 plus the velocity in that direction negative 10 because it's south multiplied by the change in time 2, which will give us 780 kilometers. If we use the vector equation, the x and y component of our final position is going to equal to the x and y position of our initial 150 and 800 plus the time multiplied by the vx and vy component of our velocity, so that's 40 and negative 10. And what we do is we just add the top together and add the y coordinate together, x and y separately. So 150 plus 2 times 40 and 800 plus 2 times negative 10, giving us an x and y position for our final point being 230 and 780 kilometers. So I have the units incorrectly there. It should be kilometers, and x should be in the east direction and y should be in the north direction for our final displacement. Now this is an application type question when it comes to vectors, but mathematically if you have a line which starts at position A and ends at position R, and let's say it has a direction vector which has an x component of bx and y component of by, then for our parametric equation we are going to have the final x position is equal to the initial position plus t multiplied by bx, and our final y position is going to be our initial y position plus t multiplied by by. For the vector equation, the x and y component of our final position vector is equal to the x and y component of our initial vector position plus t multiplied by our direction vector. In these equations, position vector r, which is represented by x and y components, is a position vector of any points in the line. The position vector A, which is represented by x naught and y naught components, is a position vector of a particular point on the line. Vector B, which is represented by bx and by components, is a direction vector of the line. And t is a real number, and it helps us to get an understanding of how far away our final point is from the initial point. And this value could be both positive and negative. Note that if we were to draw our direction vector, it will have an x component bx and y components by. The t value, if it was positive, it means it's going the direction of our position vector, and if t was negative, it's going in the opposite direction. The slope is rise over run, so that's by over bx, and that is a slope of a line which is parallel to our line. And if we want to slope of a line which is perpendicular to our line, that's just negative reciprocal, so it's negative bx over by. The summary of the video is fast forwarded here, so if you want to pause and write any of the information, please feel free to do so. And now we're going to look at a couple of examples. For the first question, we want to state the direction vector for a vertical line and for lines that are parallel to these two lines. For the first one, we can draw it out. A vertical line is a line that goes in the y direction, so it doesn't move in the x direction. So in terms of direction, in the x direction it's 0. In the y direction, it could be anything. It could be 1, 2, or any positive values. It can't be negative, because if it's negative, it's going downwards. It does have to be positive, and any of these answers would be correct. For part B, you can write this in vector form, or just you can identify the point right away. In vector form, this is xy with initial point 3 and 2, and it's being added to t multiplied by negative 1 and 3 in the x and y direction. So the direction vector will be negative 1 and 3 for this one. For the next question, our slope is 2, so it's going to be 2 over 1. And if we were to draw a direction vector, it will have an x component of bx and y component of by. The rise over run is the slope, so that's by over bx. So our b vector is going to have x component of 1 and y component of 2, and that's our direction vector. For the next question, we want to determine the parametric and vector equations for a line that goes through points A and B that are given here. It's always nice to try to visualize the question if we can draw it out. So in this case, we can kind of sketch the points. Point A is going to have coordinates of 3 and 4, and B is going to have -1 and 2. And we're going to have a direction vector. It doesn't really matter if we go from B to A or A to B. So our direction vector could be BA. And that means we're going to take all the coordinates of point A and subtract them by point B. And if we do that, we will get 4 and 2 for our direction vector. If we choose our direction vector to be AB, then we will take all the coordinates of point B and subtract them by A, getting -4 and -2. For our parametric equation, its x component of any point is going to equal to the x component of a particular point. Let's choose point A's x component to be 3 plus t multiplied by the x component of our direction vector, in this case 4. And the y component is the same. The y component of point A, 4 plus 2, which is the y component of our direction vector multiplied by t. Once we have all the variables, we can write the vector equation as xy is equal to 3, 4 plus t multiplied by the direction vector, which is 4, 2. Note that there are an infinite number of solutions for this question. We could have chosen points A or B for our initial point, and we could have chosen our direction vector to be AB, BA, or even a scalar multiply of them as well. And those would all give us a correct solution. I have prepared 3 questions for you folks to try out on your own, and I will try to post the full solutions to these questions as soon as I can on a separate video. I hope that this video was helpful in giving you an idea about parametric and vector forms of equations for a line. And in mathematics, form is a huge concept, and you can write same things in many different types of form, and each form has its own advantage. And in grades 7, 8, 9, we kind of focus on the equation of a line that involves the slope and the y-intercept, and now we're looking at it in terms of vectors. We're seeing that we can give the direction of a vector, and we can give an initial point, and now we can also kind of give a direction to a line as well. So different forms, and the next lesson we will focus on 2 other forms of lines as well. Thank you for watching.